This is solutions to test number 2. We're up to problem number 8. We have a 7.00 kilogram object being pulled up an incline by a rope. The incline is 30.0 degrees. The coefficient of static friction is 0.430 and the coefficient of kinetic friction is 0.320. The object is moving upward, accelerating at 1.10 meters per second squared. What is the tension force in the rope? So we can start by drawing a picture. Okay, there we go. Now, what kind of a problem is this? Well, again, we've got friction involved, so it's probably not an energy approach unless we're trying to track the amount of energy that's lost. All the forces are constant, right? There's going to be like gravity, there's going to be the pulling force, of the tension force in the rope that we're asked for, and we've got normal force and we've got friction. These are all going to be constant forces, so we can use just the usual F equals ma approach on this problem. All right, so that means we draw a free body diagram. So we have our object. We're going to have, of course, gravity straight down. We're going to have the normal force. We're going to have the tension of the rope. And the object is moving upward. So we have friction going downward. And by the way, the object is definitely moving. That's not even a question. So we can totally ignore static friction. That's just not playing a role in this problem. It's all going to be the kinetic friction. Okay. Now, as usual, we can put a tilted coordinate system on here when we're on an incline. That's always what we do, as shown. And gravity then is the only, quote, diagonal, unquote, force. And so we split up gravity into horizontal and vertical components. It would have a vertical component. Now, that angle theta always shows up right here in this picture. So this will be Fg, that's theta. This will be Fg cosine theta. And then the vertical part will be, to fit it in there, that'll be Fg sine theta, right? It'd be down here, but I can just move it up here as well. Yeah, so there we go. Now the vertical, we know this object does not move vertically, so these two cancel each other out, and we probably don't even have to write that down. So we do the horizontal, F equals ma. And we have three forces in the horizontal direction. We have tension going in the, let's call that the positive direction. So we have tension. And then we have gravity, a component of gravity going in the negative direction. And we have kinetic friction. And these all have to equal ma. Okay. Now we have an a, so this is not 0, as it sometimes often is, but we have it, so it's fine. And in fact, I think we have everything in this formula except ft. So if we move everything over, we solve for ft, we got the ma, and then we've got plus Fg sine theta plus kinetic friction. So again, ma, of course, now we put in our force formulas for gravity is mg sine theta. And then for kinetic friction, so actually for kinetic friction, the vertical component does play a role, but we've already figured that out, and we can use our convenience formula that applies whenever you're on an incline, and the only vertical forces are the normal force and, you know, a component of gravity. There's nothing else that's pushing or pulling in our vertical direction. And so that was mu k mg cosine theta. That was our convenience formula for kinetic friction. All right, and then you just plug everything in because we have everything here, which looks like that. And this all comes out to 61.0 newtons. Okay. And so conceptually, so the rope has to be pulling with a force of 61.0 newtons. It has to overcome, of course, part of gravity going uphill. It has to overcome friction, and it actually has to do a little more than just overcome them, because it also has to accelerate the object. And so those are your three pieces here, and that's what it adds up to. Okay. We move on to problem number 9. A 1.00 kilogram glob of Play-Doh moves to the right along a frictionless surface at 12.5 meters per second. It collides with and sticks to a stationary block of mass 3.50 kilograms. How fast will the block and Play-Doh move after the collision, and in which direction? Okay, so what kind of a problem is this? In this problem, we do have two objects that can move. One object isn't moving at first, but it clearly can move. Two objects that can move, and they're colliding. So this is a kind of a straightforward collision problem from Chapter 8, and where we're using the speeds, the velocities beforehand to predict the velocities afterward. All right, so now we have to identify what kind of collision it is, right? We have elastic collisions, we have inelastic, we have perfectly inelastic. The fact that these two objects stick together tells us that it is perfectly inelastic, which means it was one of the two cases where we could predict the final velocities. And of course, because they stick together, there's only one final velocity, because after they stick together, they move together. All right, and the tool was conservation of momentum. So the momentum beforehand equals the momentum after the collision. Now, the momentum beforehand would be the mass of the Play-Doh times the initial velocity of the Play-Doh. Because the block has zero momentum, so I won't even write it. And the final momentum will be the total mass, because they stick together, so it'll be one thing now. So we'll add together the total masses, and I'll use a capital M here, times just the final velocity. Okay. We'll zoom to the right. I should draw a quick picture. Okay, there we go. There's the initial position, the initial situation. Here's the block, here's the Play-Doh coming at it, and then they stick together, and they're going to move. Now, of course, we'd be very surprised if this thing ends up moving to the left, right? So it's got to be moving to the right, we figure. Just probably not as fast. All right, so here we go. So we're solving for VF. So VF is the mass of the Play-Doh times the velocity, the initial velocity of the Play-Doh, divided by the total mass. We plug in the numbers, which looks like that. I'm putting in a positive velocity for the initial Play-Doh velocity, 12.5. And notice I'm putting in the 4.50 kilograms, because it's 1.00 plus 3.50. That's the total mass of this combined object. And that ends up giving us a positive 2.78. And that's meters per second. And the fact that it's positive does mean that it's going to the right, as expected. So it'll be going 2.78 meters per second to the right. Conservation of momentum. This little piece of Play-Doh is moving faster. Now when they combine, it has to be the same amount of momentum, but now there's more mass, right? More mass, so less velocity, so it's still the same amount of momentum. So it is going slower after they collide. So that all makes sense. Okay. Number 10, object A of mass 250 grams traveling to the right at a speed of 0.50 meters per second collides with object B of mass 400 grams that is initially at rest. The collision is elastic. What are the speeds and directions of the two objects after the collision? All right, so just like the last problem, again, we have two objects. They are colliding. There's no external forces. So this is a sort of Chapter 8 collision problem. Difference in this one, though, is that we're told that it is elastic, which means that energy is conserved, and that gives us an extra equation along with conservation of momentum, which definitely holds. So we have conservation of momentum and conservation of energy, and between the two equations we can solve for the two final velocities. Because again, in this problem, unlike the last one, they don't stick together, so there's not one final velocity, there's two final velocities. So we have the two equations. I'm not going to write those down because we already, in fact, we didn't even do the algebra. I just gave you the final solutions, and that's what we're going to use. So the convenience formulas that give you the final velocities in an elastic collision. Okay, here they are. And it really is, once you just identify that that's the kind of problem we're dealing with, it's just plugging things in. We do know that object B, and sorry, I'm using, on our formula sheet we had objects 1 and 2, but in the problem we have objects A and B, so we'll just make that obvious connection. Object B is initially at rest, so V2I is 0. So actually these two terms are both 0, so it's really just this part. And you just plug everything in, and here we go. So they'll look like this. One thing, notice that I'm putting in a positive 0.50 meters per second because object A is moving to the right. The other thing is I left it in grams. You can, of course, switch to kilograms, but since we're just dividing mass by mass, this is just going to be a unitless number. So it actually is okay if we do grams over grams or kilograms over kilograms. This will come out the same. You didn't have to know that that was okay. You could have converted it to kilograms just by putting decimal points in front of all of these 250s and 400s, but it'll come out the same anyway. And what I think you get is negative 0.12 meters per second and positive 0.39 meters per second. So the object A will be going this fast. It'll be going to the left. That's what the negative means. And object B now, which was stationary, is now moving to the right because it got hit, and it's going that fast. Okay, and so that's the idea. Problem 11 asks, of the two collision problems that we just did in a row, number 9 and 10, in one of them energy was lost. Which one is it, and how much energy was lost? So here you had to know that elastic collisions mean that you do not lose energy. That's by definition what elastic means, that there is no energy loss, and that's actually what allows us to get that formula we just used. Conservation of energy gets algebraically inserted along with conservation of momentum. So yeah, energy is not lost in that one. So it was the earlier one, the number 9, where energy was lost. And in a perfectly inelastic collision, in fact, you don't have to know this for this problem, but it's actually the most amount of energy you could lose. So number 9 was the one. Now, how do we figure out how much energy was lost? Well, these are just the Play-Doh and the block just horizontally. There's no springs involved. Everything's moving horizontally, so the gravity is not. Height is not changing, so there's no potential energy situation going on. All the energy is just kinetic energy. So we can figure out how much kinetic energy there was in the beginning and how much kinetic energy there was at the end, and we'll see that there's a difference. You'll see it, and then you'll know how much was lost based on the difference. So the initial kinetic energy, 1/2 mvi squared. Remember, it was just the Play-Doh that was moving. The block did not have any motion, so it does not have any kinetic energy. So we plug in the numbers. It is 1.00 kilograms in that problem, and the initial speed was the 12.5 meters per second. And we have to remember to square that. And that actually gives us 78.1, and that would be joules. That's energy, joules. Okay. Then they stick together. And let's figure out the kinetic energy of the combined object at the end. So now they have a mass of 4.50 kilograms. And the speed, so we actually use our answer from number 9, which was 2.78 meters per second. And that works out to be 17.4 joules. So we can clearly see that energy was lost. So the energy that was lost, if you subtract those two, was 60.7 joules. And so that had to have gone into heating up the Play-Doh, heating up the object, and maybe sound, something like that. but that energy is no longer mechanical energy in the system. It's gone into this internal energy. All right. By the way, if you did exactly this calculation for number 10, initial speeds, do one half mv squared on object A and object B. Well, object B wasn't moving. But then final speeds, do 1/2 mv squared for object A and object B. Put them together. You will find that they have exactly the same amount of kinetic energy before the collision as after the collision. So, and therefore no energy will have been lost. No mechanical energy will have been lost. So that was built into these formulas to make that happen. All right. Okay, so that's the answer to number 11. I will stop this video and go to a new video for the remainder of the test.